CatStrong, and we repaired in Kentucky a little over 40 bridges, and the repairs have been carried out with the district folks, along with sometimes some subcontractors. Again, this is the work of many people, and but I would like to take the credit for it all the time. So, in the structures group right now, there's Dr. Piers, who does basically 99% of the work in the field with many of the district groups, and most of you may have met him before. So, as an introduction, I'm just going to be highlighting what is FRP composites if you have never worked with it, and going into the use of FRP in new bridges, and then concentrating more on the repair of bridges with it. So FRP composites stands from fiber reinforced polymers, right? And we have all used them actually. And the makeup of these FRP composites is from primary components are resin and reinforcements. In resins, there are two types. Most of us are familiar with the polyesters, epoxy, and vinyl ester. And these are the primary three resins that are used in civil applications. The polyester is used when producing shapes like the steel I-beams and so on, but made out of glass fiber or carbon fiber. The epoxy is used when we're doing wet layup, like carbon fabric or glass fiber fabric. And the vinyl ester is used primarily in rebars that are made with glass fibers or carbon fibers. The thermoplastics, we don't really use them in civil applications. The difference between these two is that in thermosetting polymers is basically like an egg. If you boil an egg, you cannot bring it back to its original shape of the yolk and the sac. But with thermoplastics, just like butter, you put it in the fridge, it's solid. You put it at room temperature, it becomes soft. Put it back in the fridge, it becomes solid. And this is primarily what thermoplastics are, but these are not applied in many of our civil applications. And reinforcements, there are many varieties, including natural fibers such as hemp, but the primary two components that we see in our civil applications are carbon fibers and glass fibers. I'm going to concentrate primarily on carbon fibers, since this is what we use for bridge repair. Carbon fiber comes to us in rolls, just like a spool of yarn and so on. That's how it comes to us. And each yarn thread is made up of hundreds and hundreds of these carbon fibers. The carbon fiber is about 1/6 to 1/10 the diameter of a human hair. And by far the standard for carbon fiber, we call it the Torres 700. And this is a medium to high strength carbon fiber. And if you take a square inch of this, it can carry over 700,000 pounds. So, and it's extremely lightweight. So you can see the advantage of these materials. They're very costly to produce because they have to pass through many furnaces at very high temperatures to get to the carbon fiber. But we have all seen them used in sports equipment and automotive, as well as in airplanes. The 787 was the one that ushered in the lightweight airplanes for carriers. And if you look at the skin of this airplane, over 80% of it is made up with carbon fiber. All the dark blue areas, this is carbon fiber. So of course, they optimize the use of the different materials. They have a number of major materials that they use on the airplanes, but by far the majority of the skin is made up of carbon fiber. And that's what makes it about 30% more economical to fly than other airplanes that came before. And of course, the primary use of the carbon fiber started with the defense. The Nighthawk, which is a stealth jet, the skin is made entirely of carbon fiber, and the shape of it including the shape of it, make it almost, you cannot see it on a radar screen. And the stealth bomber, of course, it's also made up with the carbon fiber. And it goes into many other areas, from submarines to ships and so on. Now, for new bridges, Kentucky is by far one of the leading states in using carbon fiber on bridges. And in new bridges, although it's not the topic today, we have had 6 bridges in Kentucky where, that were built from the start with some of these materials, glass fiber and carbon fiber. And each one of them was either #1 in the world or longest in the world, and so on. So each one broke some records and so on. The Clear Creek Bridge is the one that we started with. We received a grant from the Department of Defense in the early 1990s, and the bridge was completed in 1996. This is in Bath County, and it broke so many records at the time and received hundreds of articles all over the world about it. So then this bridge in Johnson County is when it was completed, it was the longest bridge in the world that had FRP material on it. The entire superstructure is made with FRP. And again, hundreds of pictures and articles were written about it after it was completed. This bridge in Clark County used carbon rebar, and it was the first in the US. Actually, it is the first in the world. I have not seen yet anywhere in the world where they started with the carbon rebars in a bridge deck before 2002. So, and this is a young man at the time, one of our students, who was holding these rebars. He can actually hold 5 times of these rebars in one hand. And the next day he had this picture in the newspaper. But let's talk about bridge retrofit. Carbon fiber, there are many manufacturers, and the fiber itself can be the low end, which is very inexpensive, about $15 a pound, to the high end, which is very expensive, about $200 a pound. So you can pick and choose what type of carbon fiber you want to use, right? And they usually they weave them in fabrics as such for the repair part. And basically it's just as the fabric on your shirt. But and we do a lot of testing in the laboratory on it. The advantage of the carbon fiber is that if I wanted to carry about 3,000 pounds, I will need a steel plate that's about 8.5 times as thick and about 37 times the weight of the carbon fiber. So you can see the advantage. Not only the carbon fiber is very strong, it's extremely lightweight and it's flexible to apply on a structure. Right? Of course, before we can use it on any structure, we have to do extensive testing on it. And we did a lot of that in the early 90s in our laboratories. In here, we have to test these specimens until they fail. And we have to be able to guess all the modes of failure, because we want things to fail in the laboratory, not on the real structure. So when we look at the types of failures, when we have these materials, we can identify 7 major modes of failure in there. By far, the majority of the failures occur in these 3, three in here, not C, D, and E. But based on these failures, design codes and guides are written. So the American Concrete Institute has a design code for designing with these materials, and the AASHTO also has a design guide for designing with these materials. Actually, as we speak, we are updating this guide for, we're updating the AASHTO guide for the repair, and we have a contract with the national academies on that. We should be done with it by the end of this year, and most likely it will be published in 2021 or early 22. So as retrofit, we started first with, in 2001 was the first bridge that we completed for retrofit. And this was before we started with CatStrong. We learned quite a bit from these projects to permit us to develop the CatStrong that we use today. This is the bridge we started on. It is in Carter County. This bridge, there were extensive shear cracks in the superstructure, and basically the state was going to replace the entire superstructure. At the time, David Steele, who was in charge of maintenance, was one of my students, and I took them to the lab, and he asked me to show them how we are testing these materials, and he asked me if we could use this on a real bridge, and I said, of course we can. And Jimmy Simpson also was the maintenance group at the time. He was also a student. So he ended up working on this project with me. So the issue that was with this bridge is that the cracks were growing really at an alarming rate, and the state decided to replace the entire superstructure. The cost was a minimum of $600,000 plus, again, we're talking in the late 90s then, and they were going to close the bridge to traffic. We proposed to repair it for $105,000 and keep the bridge open for traffic. So the way we do the repair, first we do the analyses to estimate what are the deficiencies, and then here anything you see in red is deficiency in shear, and this is at this support 2. So based on the deficiencies that we evaluate, we begin our design and identify the layout of the fabric that we're going to be using, and we finalize it. Now, carbon fiber is very expensive, so we want to optimize its use as much as possible. The way you apply carbon fiber fabric is just like you're applying wallpaper. You start by cleaning the surface, and if there are any cracks, we inject the cracks, and then we fill any void on the surface. Then we apply a primer. Then we roll the fabric on, and actually you just roll it with a roller. It's very thin. This was very thin fabric at the time, and was the best that you could get. After we finished, we painted the outside, so people would not be looking at the black fabric in there. And we monitored the bridge for 3 years. Now remember, this is in 2002. People could not believe that something as thin as this material can really save this bridge from those cracks. We put crack gauges at each and every crack and on both sides of the beam. And on the inside, the repair looks as such. And the crack gauges, we have not seen any movement in these crack gauges since 2001. So which means that the repair has done its job. But even at now, in many states, people who are not familiar with these materials call this smoke and mirrors. And I wouldn't blame them. It's something new, something that's unbelievable that this can really resist that much force. But again, the proof is there. We've been almost 20 years now, and this bridge is still holding very well. So we saved the state over $500,000, and we have not seen any cracks anymore in this bridge. But more importantly, there was no traffic control whatsoever on this bridge. So again, this received a lot of attention nationally as well as internationally on this bridge. Now, not only can we repair these beams and so on, but there are many facets of these fabrics that are really very good in repairs. This is the elevated portion of I-65 in Louisville as we approach the Ohio River. Right? I'm going to highlight this section. The pedestals in here were really cracked, extensive cracking in them actually. And when you start removing the bad concrete, in some cases, we ended up removing almost 90% of the concrete in that pedestal. The original shape of the pedestal was something as such. And when we removed, from one of them, when we removed the concrete that was cracked and crumbling, we were left only with a very small portion in here. So what we wanted to do, we wanted to confine the concrete to make it very strong and resisting compressive force. So we end up reshaping the pedestals, and we confined them with carbon fiber. And this really was quite a success. I mean, it reduced any additional, I mean, first of all, it took care of any damage to these pedestals. And another portion of I-65, we had these pre-stressed concrete beams that had some cracking right about a foot away from the pier cap. These cracks are generally due to temperature and shrinkage. And we had about 120 locations on beam ends that had these cracks, and some of them were severe. But what really was very confusing to us at first is, why are they all forming about a foot from the pier cap? And there were no plans for this bridge. Finally, one engineer, an old-timer, told us that they used to use these double bars between the two beams at the ends. So, and that ended about 1 foot into it. So that basically initiated, all the cracks initiated at the tip of this double bar. Some of these cracks were very severe, that one option was to build, in one case, an entire pier about maybe 4 or 5 feet away from the existing pier, and others basically increasing the support using from the pier cap and so on. But these were 120 locations and along the entire elevated roadway. So the cost would have been really prohibitive to do that. So we decided to monitor the cracks and to see how they move with time. And what we found out is that the red line is how temperature increases, and the blue line is how the crack is moving horizontally. So the crack was constantly moving, and actually you can see it with the naked eye if you are standing under the roadway. I-65 trucks are constantly on it. So, but we were able to monitor it for a whole year because we didn't see any danger at the time of any collapse of a beam, because we were able to monitor it, and we noticed that the crack really is not growing. So we designed a retrofit such that it will be the least expensive approach to this repair. We decided to close this crack and move any future cracks away from where the fabric ends, somewhere in here. This is a much safer area to repair on the beam as opposed to the one right near the support. So, and when we did that, we also monitored it for another 3 years to see what's happening. What we found out is that on the left side in here, the crack was moving quite a bit before we retrofitted it. After we did the retrofit, the crack is barely moving in here. So the repair was successful. But even to this day, we have not seen any cracks go beyond where the fabric was repaired. So for less than $200,000, we were able to repair 120 locations on that bridge and really saved at least a couple of million for the other alternative. This is also on the elevated highway, and this pier had quite a bit of spoiled concrete, and some of these steel rebars had lost about 50% of their area due to rust. So we usually, the way we repair these things is after we clean everything and the steel, etc., we apply fabric in the longitudinal direction, and then we come back and wrap the pier. We decided to use what's called the Tri-Axial Fabric. This is used extensively in aerospace industry, both for civil aviation as well as military aviation, right? So this Tri-Axial Fabric has fibers that go into 3 directions. So that saves us quite a bit of time, because with one fabric, I can provide reinforcement for both the vertical direction and the hoop direction around the pier. And this was the first time ever that such a fabric was used on any civil structure, and also received quite a bit of attention in Another method for repairing with carbon fiber is what we call laminates. These are pre-cured plates, basically, that come to us in a roll. And this plate would be equivalent to a steel plate that's about 7 times as thick. And of course, weighs about 30 times more. So this whole roll can be carried easily with one finger. So we did, again, extensive testing in the laboratory on it and collected data from it, right? And to give you an idea on this beams, we tested one beam originally without any laminates on it, just plain concrete, reinforced concrete. And let's say it failed at 100,000 pounds. We took that completely damaged beam, straightened it, repaired the concrete, and put the laminates on it, and it failed at 150,000 pounds. It was 50% stronger than the original beam. So the material works very, very well. And it has been proven not only by us in the laboratory, but by many researchers all over the world. So the first bridge we repaired with this was the Louisa Fort Gay Bridge. And this bridge sees quite a bit of haul trucks, and some of them using weigh in motion weigh over 200,000 pounds. And the legal limit is 126,000 pounds. So the bridge is carrying close to double what it's designed for. So of course, we're gonna start seeing cracks and so on in the beams. These cracks are really not that serious. Usually we don't do the repair with carbon fiber for these cracks. But the problem was that every month we used to go to inspect the bridge, we see more cracks forming on the soffit of the beams. And since this bridge is really very critical for both the Louisa and Fort Gay, the state decided to retrofit it. So we are using this laminate to do the retrofit. So we do, of course, all the analyses first to see how many of these laminates we need to use. We start preparing the surface, apply the laminates, and this is the finished product. We don't use this material anymore. It has many downsides that I won't go into. We use a lot of fabrics these days. It's a much better performer. But at the time, this was the material for repairing these types of bridges. So based on our experience with the 10 bridges that we repaired, with these laminates, you have to apply them as one piece. You can, I mean, of course you can splice them, but if you splice them, it really weakens the entire retrofit. So we never splice these laminates. So basically you have to be able to reach the bridge and to have at least 2-3 people carry it to put it on that bridge. We did one bridge repair in Scott County with the ultra high modulus laminates in here. For example, for the Louisa Fort Gay, it takes quite a bit of time to put that laminate on the soffit of the beam. And the problem we have is that when you are applying these materials, the resin that we use has a pot life, and that pot life is 70 minutes. Actually, if it takes you 20 minutes from the time you mix the resin to apply the laminate, you lose about 40% of the capacity. So for this reason, we don't really use it anymore, because anytime you are mixing these resins to apply them, many times it takes us 30 minutes at least to apply the material on a bridge. So from 2011 to 2018, of course, the research started in the early 2000s, but field applications in 2011. In our laboratory, we after testing about 11 different types of these panels, we decided on these types of carbon rod panels. Right? These panels, we made them 4 foot wide. We can make them actually any length because these come to us in miles of rods. We cut them to 4 feet and then place them on a backing. So it's easy to be carried by one person from a bucket truck, basically. And the way these are done, we connect them at a finger joint to provide the continuity. So now I can be hanging from a bucket truck over a waterway, strengthening the underside of a bridge with these things. It's an extremely effective method for repair, and we did extensive laboratory testing on it in our lab, primarily to evaluate this finger joint. And to give you an idea, our strongest panel can carry 195,000 pounds in a foot width. This is equivalent to a steel plate that weighs 26 times as much as the rod panel. And so, of course, quite a bit of an advantage. The other advantage of that rod panel is that at the time we developed it, the best fabric to use, I would have required 4 layers of it to be applied. Now, this doesn't seem like much, but to apply the 4 layers, that means it's over a period of 4 days, while I can do this in 1 day. So, of course, the labor cost is quite less with the rod panels. And since I give a lot of talks to middle school kids and high school kids, I try to show them that the width of 1 foot of a panel can carry all these trucks. So, of course, we have to do a lot of laboratory testing to validate anything that we use. So we did extensive laboratory testing in here. Now, for us to do the testing on one beam in the laboratory, if I'm doing a whole series of them, it actually cost us about $10,000. I know concrete is cheap and everything, but you have to instrument it extensively, and then we have to reduce the data and the setup and so on. So by the time I count everybody's time, every beam cost us about $10,000. So it's a very expensive process to do testing. So we do a lot of computer modeling, and we model the carbon rod individually and the concrete, etc. We can do a lot of testing on the computer, and it doesn't cost us that much. So, but in order to validate the computer model, it has to be validated with the testing part, so they have to be able to mimic each other very carefully. And any localized failures, such as the one we saw on the previous slide, we highlight it even more to identify where the failure initiates and why. So once we do all that, this is the failure for one beam where we put some wraps around the ends of the fabric. And now I'm doing the computer testing for it. And actually, you can see it slowly moving. And when this fails in the computer, it actually just fails just like it did in the laboratory. So now we are confident with our computer model, and I can test hundreds of these beams very cheap compared to each one costing us about $10,000. So we started a number of repairs. The first one was in 2011. And on this one, as you can see, this is still very elementary the way it looks, but it does the job. I mean, it has nothing to do with the strength. And these rod panels were built by, or were constructed by our students in the laboratory. And this is the second bridge. And as it happened, this is on the Bluegrass Parkway, the 2 students who built the rod panels for this bridge lived south of this bridge. So every time they drive back home and back up, they see their work on the bridge. So in this bridge, it had an impact, and one of the rebars was damaged. So basically what these rod panels do they replace the capacity of the damaged rebars. And once we are done with it, you really cannot tell that it was repaired. I mean, of course, the gray here is not identical to the concrete, but as you're driving underneath it, you can barely notice it. This bridge is in McLean County. And this gives us an idea on the steps in the repair stages that we go through. By the way, all the bridges I've shown so far, except one, have been repaired by the district crews, the bridge crews or maintenance crews. Now, in this bridge, the concrete, original concrete was down to this plank. And when we first looked at it, the concrete was down to where the rebars are. So in order to do the repair, we have to remove all the bad concrete. We cannot leave any of it in there. And then we have to clean via sandblasting or brushing, etc., the rebars to go back down to the bare steel, and then we protect the steel. And then we fill the concrete back to bring the beam back to its original shape. So after we bring the beam back to its original shape, what happened in here is that the steel, some of the steel rebars lost about 70% of their areas. So, which meant that, of course, we have to replace that steel. So we could replace it internally or externally. So if we use the rod panels, we can replace the steel that's lost externally. We put some on the soffit of the beam and some on the side of the beam. And it had lost also some shear capacity, and these fabrics in here are for additional shear capacity for the beam. So again, all the reinforcement now, instead of being inside, is on the outside of the beam. And this is the finished product. Now, we don't only repair beams, we also repair abutment walls. This was a crack in the abutment wall. Again, the steps are to fill the cracks, and then we apply the fabric on it. And basically that holds the crack from growing on this side. It's very difficult, of course, for us to go back to the back side of it. So whenever we do a design for the repair, we have construction specifications or repair specifications. This is on UK's campus, and there's tons of them. A lot of the steps you see rusted rebars and concrete spalling. And I mean, this is very typical, not only on our campus, in many other areas. But look at this, these steps. These were already repaired with some of the best concrete you could buy at Lowe's. But what they failed to do, they failed to clean, they failed to remove the bad concrete and clean the rebars. So after a while, that repair also failed. And it will fail. And I've seen many cases where they used carbon fiber to repair something, and after a year or two, they started debonding from the structure. The reason is not that the carbon fiber or the resin are bad. Actually, they are very strong. The problem is the manner in which they did the preparation. So with our designs, we really don't let anybody just use the material without our supervision or training that they have gone with us before, because 99% of the success of any of these repairs is how you prepare the surface and of course first do the repair of the concrete and prepare the surface. This is a bridge over I-65 that was impacted. Of course, we cannot close the freeway underneath during the day, I mean, except for inspection at this time. But for the repair, we did the repair at night. And I'll take you through this process. The way we do the repair is first, we evaluate the capacity of that beam as it was built originally. And then we evaluate the capacity of the beam when it was impacted. So it's reduced quite a bit in here. And then we evaluate the capacity of this beam when we strengthen it with CatStrong. So it goes quite a bit higher than the original capacity with the CatStrong in there. But of course, with design guides, we put limits on a number of things. So we do all this evaluation, and then we do the design for the repair, and then we oversee the repair. So if you've repaired concrete, you know, you follow geometric shapes to be able to place the new concrete in there. You sandblast the strands in this case and put coating on them. There were, you can see this strand comes this way and it's bent that way. And this is actually was cut. There were about, I believe, 3 strands that were severely damaged on this. So we cannot really come back and put new strands in there with ease. So we're gonna reinforce it from the outside. So after we did all the repair, we filled the concrete back to bring it to the original shape. And of course, there's gonna be areas that did not fill properly, so we come back and patch these. And then we fill the cracks. We grind the surface to make it very smooth, so the bonding of the resin and the fiber is perfect to the concrete. We want the failure to occur inside the concrete and not at the bond region. I would like you to think if you're putting a Band-Aid on your hand. If your hand is a little bit oily or dusty, when you put the Band-Aid, it doesn't really stick on your hand, it easily comes off. But if you wash your hand very well, and it is dry, and then you put the Band-Aid, it will stick to it. The same thing, so the Band-Aid is very good. It's just that you may not have prepared your hand for the Band-Aid properly. And that's the same thing that goes when we're applying these carbon fiber materials. So we have to grind the surface very well, and then we sandblast it to remove anything that may have been, like as cars are driving underneath, they may have emitted some oil that may have stuck on it, all that we remove, right? And the night before we apply the, when we are applying the material, we either sandblast it again or do airbrushing for it, and we start applying the resin, and then we apply the rod panels. Now, each one of these carries 195,000 pounds, guys. So over here you have close to 380,000 pounds of force being applied to make up for what's lost with the strands. And then we cover the beam with this. This tri-axial fabric is that if there's another impact on the bridge, it will hold all the crumbled concrete inside and would not fall on the traveling public, basically. And this is the finished product. We've done this on many other bridges. I'm just gonna go quickly over them. And here I'm gonna say that one of the advantages of using these rod panels is that if we were gonna quit, let's say this was 2 in the afternoon and we're gonna stop here, we can have a cold joint and come back the next day and continue from. So it's very easy. And then we switch to the next lane. We closed only one lane on this 2-lane freeway. And then the next day we closed the lane we worked on and worked on the other lane. So it gives us quite a bit of flexibility when we're doing these repairs. Now we are primarily using fabrics. It has a lot of advantages from handling and so on. We have a tri-axial fabric that we use extensively, but more importantly, we have this heavyweight fabric that we worked with the manufacturer to produce it for us. And this heavyweight fabric, 1 inch of it, or I should say 1 inch carries 10,000 pounds, or a foot 120,000 pounds. I will need a steel plate that's a little over 9 times as thick and more than 70 times the weight to produce the same capacity. So you can see quite a bit the advantage of it. And that fabric comes in a roll like this, that's, you can easily carry this entire box. Actually, you can carry 3 or 4 boxes up. And it is really very strong. So imagine having steel being rolled in at 9 times the thickness. And again, for middle and elementary and the high school kids, I show this thing to show them how much force it can carry. We've done a number of these bridges in Kentucky with it, and I will highlight some of them. We do box beams. This one is in District 4. And the cracks on these beams were really, did not fit, for example, flexural cracks or shear crack or torsional cracks. They were going everywhere. After evaluation, what happened is that they were settling on one side of the abutment and the entire bridge was twisting. So there were many forces coming in to produce this. So we couldn't really use just any unidirectional fabric. We needed tri-axial fabric to be able to cover all these cracks. So we do the design and the repair process, and this is the finished product on all these ends of the beam. I'm going to highlight this bridge. This was impacted twice, once after we repaired it. So this is over I-71. This is in 2014 impact. And one of the rebars was heavily bent out of shape that we had to cut it out of it. And other bars were slightly bent. So what we did, we removed this bar that was heavily bent and spliced another bar in place. But we needed to replace the strength lost by these bars being bent. So since we could not do the repair right away, we usually put glass fiber mesh to protect, to make sure that no debris falls on the public until we get to the repair. As it happened, another overhigh truck came and hit that mesh. So during the repair process, we removed the mesh, we cut the bar, we straightened, we used this steel cable that goes to a truck on the bridge to straighten some of these rebars. Okay. And of course, we sandblast the rebars. Here we are putting the connector for the splice to splice the rebar. We're mixing now the concrete to fill the form to bring the beam back to its original shape. And then we clean it up and sandblast it just like we did before. And then we start applying the fabric. The fabric is being doused in a epoxy resin, and then it's being placed. It is time consuming even if you have a small repair project. The reason is after you fix the concrete and blast the steel rebars and you put the coating, you have to wait 1 day. So even whether the hole is, or whether the area you're repairing is 1 foot wide or 20 feet wide, it makes no difference. You have to wait 1 day. And then you come back and pour the concrete, and then you wait another day. And then you come back and do the cleaning up and so on. So this, although it is not time consuming in certain cases, certain applications, but you still have to wait the time for the materials to cure. So this was the finished project, and we're all very proud of it. But in 2018, I'm sure some of you saw this. Another truck came by, was carrying a backhoe, and the arm lifted off of it and just hit the bridge. So if I go over it again, you can see now where it hit it. And you can see the hole it made into the fabric and the concrete itself. Now, the state was going to replace the bridge, and they called me to tell me that the bridge was hit if I wanted to go look at it before. You know, after you repair a bridge, it becomes like your foster bridge in a way, like you're fostering a puppy or something. So you do care about them. So I went to see it, and basically the entire steel was ripped off of that beam. So the capacity of this beam is 0, basically. And every other beam was hit. But after looking at it, I figured out that, yes, we can repair it. So I had to convince them that, yes, we can repair it. So we came back with a repair plan. We just cut off all the rebars. It was very hard to remove the original fabric that we placed, which is a very good sign. We had to sandblast it. We could not chip it off, actually. So we cut off all the rebars and put connectors and connected all but one of the rebars. And this is the finished product in here. Then we formed the beams again. And we're applying the fabric on it, and that's it. The beam that was as built, that first beam that was impacted, had a capacity of 1,083 kip foot. When it was impacted, it had 0. When we fixed it, it has 1,148, which is more than the original beam. So these repairs really do work. This is another bridge I'm going to take you through. The bridge looks innocent and the damage is not that bad, but once you start removing the bad concrete, in this one, we were not done yet. We removed almost this entire portion of the concrete of these beams and also over the pier gap. So if you don't do that, there's really no purpose of putting the carbon fabric in there. It would not have. So you have to remove this entire bad concrete. And you don't really need to know how to apply these materials or do the repairs. We will be with you all the time from day one till the end. So here, these gentlemen, I mean, they were a wonderful crew to work with. They were from the detention center in Oldham County, and they've never worked in concrete, all of them, and they were able to do the repair on this bridge. This is another bridge in Louisville that was heavily damaged. Again, when it finished, the substructure of this bridge was much stronger than it was originally built. This is in Warren County, where this pier was impacted by a truck, and the damage looked minimal to the pier, but it was really heavily cracked, but major cracks occurred on the pier cap. So what we do, we know from all our lab and theoretical analyses that if you confine concrete, this would be the original strength of the concrete when it's not confined. When we confine it, depending on how much fabric I put on it, I can increase its capacity to be more than double its original, just because I confined it and I'm not allowing it to expand in this circular shape. So this is the approach that we take when we are strengthening these pier caps in there. We confine the concrete, and the same thing when we are strengthening the pier itself. So when we finished, as you can see, we have confined the pier. So actually it is quite a bit stronger now than it was originally built, the same thing with the pier cap. And when we're done, you can really barely tell that this was a damaged pier in here. And when we do the analyses on this pier, we found out that after we repaired it, it can carry 3 times the axial force as it was originally built. Well, this was one of those fun projects that we had some money left over, and the state wanted to do a repair on the Smithland Bridge in here. This crack was severe going all the way around. So to give you an idea, if I were to test a concrete cylinder and it fails at 4,000 PSI, if I take that cylinder and split it in half and wrap it with carbon fiber that we call CatStrong 120, so the cylinder is completely cracked in here. I stopped the testing at 6,000 because there were many students around us. Theoretically, this should have gone to 9,000. But at 9,000, it would have exploded like crazy, and they didn't want that. So it was 1.5 times stronger, at least, than the cylinder that was intact. So this works, and based on this approach, we've repaired the pier cap in here, as well as the pier itself. And this is the repair. The repair was carried by the district crew. Pile wraps. This is a wrap that we developed in our laboratory. The students actually fabricate them. We call them CatStrong wraps. If this is a pier, we put some spacers around it, wrap it, and fill it with concrete or resin. So some of the recent projects we finished. We have a number of them coming up. Again, this one in McCracken County, the pier caps, as well as a portion of the pier at the top, were damaged or degraded. The concrete has degraded quite a bit. And there were 4 locations where these needed to be repaired. So we developed the design for them, worked with a contractor, and carried out the repair. And this bridge, I'm highlighting it. These were some wooden piles that were very long. So we developed the system to do the wrapping in stages. And it was the first time we developed hemp fabric. And the hemp fabric, we, again, formed it in our laboratory. And we call it CG for Calvin Grayson. Calvin passed away on July 4th. He used to be the former Secretary of Transportation, very dear friend of mine. And he used to call himself Hemp Boy because he raised hemp when he was little, and his friends called him Hemp Boy. So in his honor, way before his passing, this was after him. So this is the hemp wrap. And of course, it was the first time ever that any natural fiber material was used as a construction product. So it received a lot of attention internationally. So in conclusion, if you have bridge problem, just send us a sign, guys. We have worked right now, we have repaired bridges in 11 of the 12 districts in Kentucky, and we work with the district crews. What we do, we develop the entire design, we procure all the material, we prepare the construction plans and construction specifications, and we go and work with the group, be it the district crew or a local contractor, to do the repairs. It has proven to be an extremely economical process as such. And of course, we have a lot of logos and stuff for this CatStrong. Acknowledgement, again, this, the CatStrong received US patent this in May 19, 2020, very recently. So we're very proud of that. We have given all proceeds to the University of Kentucky. Basically, everything goes to support students and product development. So we have all these groups of folks that have funded our projects. And really, these are the people that do all the hard work. And I'm the one who does all the talking and gets all the credit, but they're really the ones who have done all the hard work. And if you have any questions, I would be more than happy to answer.
Thank you so much, Dr. Harik, for joining us this morning, and thank you all for attending. If you'll notice, I put an evaluation link in the chat box, as well as our Tech Assist form. Local agencies, if you guys have any bridge questions, Dr. Harik, as he said, will help you now, but we can also get with you after to work on a specific problem or issue. I will also be emailing the evaluation form, and we send out certificates on Friday. So for right now, we will hang out for a few minutes to answer questions. If you don't have anything else, you're free to jump off here, and have a great rest of your day. Mr. Williams, I was wondering if you recognize that bridge. You're McCracken County, I think. Oh, he left.
I see Kevin Rust. Oh, I thought Kevin will be asking a question. Folks, I mean, we're available just anytime, really. Just shoot us an email and or call us. The best way we can help is if you send us pictures of what the damage is, but please take pictures from afar first to show us the bridge itself, and then as you get closer, take more pictures. And if you send us those, we'll be able to tell you upfront whether the CatStrong products can work or not. It doesn't work on solving every problem in the bridge, but when it works, we can tell you, yes, it will work. And many times, we really don't have to go to the bridge site to do the repair plans, but some cases, the pictures cannot tell the full story, so we end up going and doing the evaluation. And the way you get hired is that you will have basically a contract with the Kentucky Transportation Center. That's how we get hired, basically. And what we do the entire design. We provide all the material, all the construction plans for the repair and the construction specs. And we work with your crew or any local crew, any local contractor. So, so basically, all your hard work is going to be is to send us those pictures and having the money to do the repairs.